Okay, welcome back to conformal invariance. We're doing more of capacity today. I wanted to mention before we start, I don't know how many people have passed through the Science Center sometime in their lives, but if you have, you've probably seen some of the math posters that are on the wall there. This is one of the ones that I worked on a couple of years ago. Hang on a sec. And in case you feel like going to Kansas today, I am giving a talk at 2 p.m. Called Illustrating Infinity, explaining what these posters are about. So you're welcome to join. Okay, so I posted the Zoom link in the chat. So we're discussing the ways of measuring the size of a compact set in the complex plane. And so far we have the following definition. The first is called the transfinite diameter. This chalk. And this is defined by R infinity of k is the limit of R n of k. And Rn of k is capital Rn of k to the 1 over n. This is getting my notation mixed up. This is d for diameter. D infinity is the limit of dn, which is dn of k raised to the power n choose 2 to the minus 1. And the key is this quantity dn of k, which is the max over points a1 up to an in k of the product of the distances between distinct pairs, ai minus aj. And we saw that this was equal to the absolute value of the Vandermonde determinant, which can be expressed using monic polynomials of an arbitrary type, one for each degree. We'll use that fact plus Hadamard's inequality in studying it further. The second measure of the size of a compact set is what I call the polynomial diameter, or let me call it the polynomial radius. And this is defined by R infinity of k is the limit of Rn of k, which is itself capital Rn of k to the 1 over n rather, and Rn of k with a big R is the minimum over all monic polynomials Pn of z of degree n, so Zn plus lower order terms of the maximum of the absolute value of P of z with z and k. And then finally, we're going to introduce a third method, which is called capacity. And this will use the Laplacian. And let me just, for completeness, say up front what the definition will be, and then we'll discuss it in more detail. We look at the Green's function. Okay. From the point at infinity, in a way I'll explain. And then this function turns out to look like g of z is log the absolute value of z minus our certain constant plus something that tends to 0 as the absolute value of z goes to infinity. And then the capacity of k will be, let me make sure I have this right, will be defined as e to the gamma. And then the main theorem is that all of these are the same. So d infinity of k equals r infinity of k is equal to the capacity of k. And as I mentioned last time, there's lots to be gained by the fact that you have three different definitions of the same quantity. The first thing I drew your attention to was the fact that the dn is good for getting lower bounds, because any particular choice of these guys gives a lower bound on d infinity. Similarly, Rn is good for getting upper bounds, because we take the minimum over polynomials. So any particular polynomial gives us an upper bound. And so when these things are the same, you can play these two definitions off one another to get upper and lower bounds. And then maybe the main point is that these definitions transform in ways that are easy to understand. The capacity is kind of hard to understand, because when you change this at k, it's hard to say how the Green's function changes. So there's a lot to be gained from this three-headed monster by examining each of its heads. And in fact, the capacity will turn out to have a very elementary definition in terms of the Riemann mapping theorem in the case where k is a connected set. Okay, so let's continue with our discussion. I'll set aside capacity for the moment. And we've already proved that dn exists, and we have this definition now of Rn. So the main task is to prove that Rn exists, and that it's rather that R infinity exists, and that it equals d infinity. Okay, so any questions before we start on that argument? Okay, so let's go to prove that R infinity of k exists. So for what we do is let's, for the proof, for each n, we choose a Pn so that the max over k of Pn of z realizes the optimum Rn. And now what I'm going to observe that I can use products of these Pn's to get monic polynomials of much higher degree. And those will compete in the minimization problem for higher degree. And that will show that when the degree gets large, Rn tends to go down. So let's see that accurately. So now given any n, let's say, think of it as being much bigger than little n, we can write this big N as n times little d plus a remainder, where the remainder is between little 0 and little n, little n minus 1. And so now we can consider the polynomial q of z, which is our polynomial degree n raised to the dth power times this polynomial p of r of z. And this product will be monic of degree n, capital N, because of this decomposition of capital N. And so the minimum, the maximum of this Q is an upper bound for our capital N. So what that gives is the following statement. You'll just erase all of this. That then gives that the sup over k of the absolute value of q is less than or equal to the sup of this number, which is Rn to the d, and then R sub little r. Okay, and this on the other hand is an upper bound for our capital N. And so our capital N is less than or equal to our little n to the 1 over n rather. This is what our little capital N looks like. We normalize by taking the 1 over nth root. So this will be our little n to the d over capital N times big R sub r to the just 1 over n. And now we take the limit as capital N goes to infinity. So what happens to this quantity? Well, d divided by big N is almost exactly little n. It's little n plus r over little n. So this exponent here just converges to 1 over n. This exponent here converges to 0. So this whole quantity converges to Rn to the 1 over n times 1, which is little rn. And as we go along, it's an upper bound for big Rn. So what we get is that the lim sup of big Rn is less than or equal to little rn. So that's pretty good. That says whatever the limit of this sequence is, it has to be less than little rn. But now let's take the lim inf over little n, and that gives that this is the lim sup of big Rn is then less than or equal to the lim inf of little rn. So if the lim inf is an upper bound for the lim sup, then the limit must exist. And so therefore, Rn converges as n goes to infinity. Unlike the transfinite diameter, it might not converge monotonically, but it sort of is eventually trying to converge monotonically. That's what this argument is showing. Okay, so at least the polynomial diameter exists. Now, how do we relate the polynomial diameter to the transfinite diameter? So this is kind of cool that these two things are relatable. It's not too hard to believe because you have the zeros of the polynomial to play with. But I want to draw your attention to an important point. When we defined the polynomial diameter, we didn't say anything about the zeros of the polynomial. In particular, we did not require that they lie in the set K. So you can't just say, oh, take the zeros of the polynomial, put them inside the set K, and then play around with those as points for the transfinite diameter. So the argument, it goes a different route. So this is to prove that R infinity of K is equal to D infinity of K. So let's first show that R infinity is less than or equal to D infinity. So what we do is we choose points B1, A1 up to AN, so that the Van der Moe determinant of that gives in absolute value D sub n. This is the best we can do for approximating the transfinite diameter. And now we do something rather clever. We let Q of Z be equal to, now we do put zeros at these points. And then for good measure, we add in the product over I less than J of the absolute value of AJ minus AI. Okay, so now what's good about this? What we notice is the maximum over Z in K of the absolute value of Q of Z is something we can understand. Why? Because if you put Z equal to some number AN plus 1, then the product you get here is exactly the kind of expression that competes for DN plus 1. dn plus 1 has to do with all of the distances between n plus 1 points. So it would include the distances between n points plus this additional one. So q, the absolute value of q of z, is nothing more than the absolute value of the van der Moot determinant of z, what we put it at the end, a1 up to an comma z. And the maximum over k, then, all of these are competing for dn, so the maximum of this over z is less than or equal to dn plus 1. On the other hand, q is almost a monic polynomial. It's not monic because of this factor here. This factor here is just dn. So what that says is that this quantity is so we note that q over dn is monic of degree n plus 1. Of degree n. And so therefore, the max over k of q over dn is an upper bound for Rn. But on the other hand, it's less than or equal to dn plus 1 over dn. And these quantities, let me remind you, this is just the same as little dn plus 1 to the n plus 1 choose 2, and little dn to the n choose 2. And now recall that dn really is decreasing. d1 is greater than d2 and so on. So this is bounded by dn to the n plus 1 choose 2 over dn to the n choose 2. Now what's the difference between these two exponents? Well, n plus 1 choose 2 is nothing more than 1 plus 2 up to n. And this is the same thing except the last term is omitted. So this quotient here is just dn to the n. So we get big Rn is bounded by dn to the n, and so big Rn to the 1 over n is less than or equal to little dn. And of course, this is little Rn. Okay, so Rn is actually less than or equal to dn, and so taking the limit, we get that R infinity is less than d infinity. Okay, so that's the first step in relating these two gadgets. And it's not too surprising. It's kind of easy to take these van der Moot determinants, which involve lots of differences, and turn them into something that bounds a polynomial. What's tricky is how do you go backwards to use polynomials to bound this complicated product of differences? And I think that this would be very hard to discover if you didn't first develop the theory of van der Moot determinants as we've done. So there's a trick involved in the reverse step, and this is one of the few steps in the development of the theory where it's like solving a kind of a hard problem, like a hard Putnam problem. If you didn't think in terms of working with determinants, it would be very hard to prove the reverse inequality. So let's now prove the reverse inequality. So we already have that R infinity is bounded by D infinity. So let's do part 2, which is that D infinity is bounded by R infinity. Okay, so this is really fun. So we let P1, P2, etc. Be monic of degree n, Pn, and satisfy that the max of the absolute value of Pn over k is equal to Rn. And now comes our friend Dn. So we choose any a1 up to an, choose a1 up to an in k to maximize Dn. Now, what was dn? It was the absolute value of the determinant of the van der Waals matrix. And now comes our elegant trick. So what is this van der Waals matrix? This is the absolute value of the determinant of, and by the way, I could include P0 here. P0 is just the constant 1. So what we can do is, instead of using powers of the AIs here, as we saw when we discussed van der Waals determinants at the beginning, we can use any monic polynomial of degree n in the nth column. So we put ones here as before. That's really using P0. And then here, instead of putting A1, we put P1 of A1, P1 of A2, all the way down to P1 of AN. And then at the end, we have Pn minus 1 of A1 down to Pn minus 1 of AN. So we use this beautiful fact that the van der Waals determinant can be computed using any sequence of monic polynomials. They don't have to be the monomial z to the j. And we choose those to be the ones that enter in the definition of the conformal radius. Okay, so now what we know is that since the AIs all lie in K, we have that the absolute value of Pj at AI is less than or equal to r to the j. So that means that the size of this column is bounded, every entry in this column is bounded by R1. So if we think of this as a vector V1, this as a vector Vn, then Vn minus 1, then we get that the norm of the vector V1 is less than or equal to the norm of the vector R1 in Rn, in Cn. R1 repeated n times. And that's equal to R1 times the square root of n. Because the vector of all ones has length the square root of n. And similarly, the norm of Vj is less than or equal to Rj times the square root of n. And now we can use Hadamard's inequality that says the determinant is bounded by the norm of the lengths of the columns, the product of those norms. So Hadamard says this is less than or equal to the norm of the first column, which is square root of n. If you like, that's square root of n times R0. And then we have square root of n times R1, all the way up to square root of n times Rn minus 1. And so this is n to the n over 2, there being a total of that many terms, times, and since R0 is 1, I'll just drop that. So times R1 up to Rn minus 1. Now, it would be better if we could approximate these in terms of the conformal radii. So remember that Rj is the same as little rj raised to the jth power. So this we can write as n to the n over 2 times little r1 to the 1, little r2 squared up to little rn minus 1 to the n minus 1. Okay, so that's pretty good. So we have a bound on dn in terms of the little r's. But we're trying to control little dn, which means we should take a root here. Okay, so let's see what we can get in terms of little dn. So remember, this quantity here is just little dn to the power n choose 2. And n choose 2 is 1 plus 2 up to n minus 1. Let's call that capital N. Notice that the exponents appearing here are 1 plus 2 up to n plus n minus 1. So the sum of these exponents is the same as the exponent of little dn. So what we get is that little dn is less than or equal to n to the n over 2 capital N times r1 to the 1, r2 to the 2, rn minus 1, the n minus 1, raised to the power capital 1 over n, which is the sum of these exponents. Now, what's the geometric mean of two numbers? You take their product and you take their square root. This guy is just a generalized geometric mean. You take the product of these numbers raised to the various powers, and then you take the nth root, where n is the sum of the powers. So this is something like an average of these numbers. It's just a geometric average. On the other hand, Rn is tending to R infinity. And even more so, the weights of the later terms in the series, which are these exponents, are higher than the weights earlier in the series. So you're taking an average of numbers that are converging to a constant, and so the average converges to this constant. So this quantity just tends to R infinity, and this quantity is, well, little n over big N. Big N is roughly n squared, little n squared. So this is n to an exponent going to 0, like 1 over n. So this goes to 1, and this goes to d infinity. So that gives the reverse inequality, d infinity is less than or equal to r infinity. Okay, so that's a fairly direct, if somewhat subtle, calculation just involving triangle inequalities and determinants, and especially Hadamard's inequality in this last step. And we kind of, this can be presented in a high school linear algebra class. We haven't used any complex analysis. Okay, so the next step is to describe our third definition of the size of a set. And this will involve something called the Green's function. And the Green's function is important in its own right, and I'm kind of using capacity as an excuse to introduce the Green's function. In some sense, the main topic of this course is the Laplacian, and conformal maps, transfinite diameter capacity are all kind of subservient to and enlightening about, informative about the way the Laplacian behaves. So let's look at what's called the Green's function. So here's the setting. We want to work in a world where we know how to solve the Dirichlet problem. So let's choose a domain omega that we understand. Let's say omega contained in C is finitely connected. And remember what this means for us is that the boundary is a finite collection of Jordan curves. And this is a region where we know how to solve the Dirichlet problem. We have the extension operator, the Poisson kernel, which we proved exists by Schwarz's alternating method. So we have this Poisson kernel P sending continuous functions on the boundary of omega to functions that are continuous on omega and harmonic on the interior. Continuous on omega bar and harmonic on the interior. This is our solution to Dirichlet. Okay, now what we're going to do is easily understood from the point of view of electrostatics. We're going to put a point charge in at a particular point W in this region. And we're going to compute the potential of this point charge. And that'll be a function phi that's harmonic, a function g, I should say, that is harmonic on the whole region, but it blows up in a certain way at this point. So it's not quite harmonic everywhere, it's not harmonic at W. And this harmonic function will depend on where we put this point charge. And actually what we want to do is induce a positive charge on the boundary here. And so we put a negative charge at the point W. And then if you were to take the gradient flow would go like this. It would flow away from the boundary and go towards W. Okay, so G of ZW is by definition the unique function that is harmonic in omega minus the point W. It has the property that the Z Laplacian of G of ZW is equal to minus 2 pi times the delta function at W. That's our point charge. And then it's normalized so that G of ZW equals 0 when Z is in the boundary of omega. Okay, now why does this function exist? So here's a better definition. Alternatively, we write G of Z W as, and now we want something that has a point charge at W. So the fundamental solution for the Laplacian is given by log absolute value of Z, but we want to have a minus point charge there. So what we do is we just write G of W so that it behaves the way we want near the point W. So this function blows up, it goes to positive infinity at W, as Z goes to W. And so it solves this equation here. Now the problem is, how do we normalize our function so that it's 0 on the boundary? Well, notice that this equation is very ambiguous in terms of G. We could add any harmonic function to G and it would still have the same Laplacian. So what we do is we add here what I'll call phi W of Z, where this is harmonic. Actually, maybe I'll subtract phi W of Z. And what do I choose for phi W of Z? I just let phi W be the Poisson kernel applied to the function 1 over log Z minus W. So in other words, you plop down this point charge, and that gives you some well-defined values on the boundary of your region. You then take the harmonic extension of this function, restricted to the boundary. This is a perfectly nice function on the boundary since W is in omega, not its boundary. And you extend that to the interior, and then you subtract it off. And since this extension agrees with this function on the boundary, the difference is 0. So you just compensate by a harmonic function to normalize so the Green's function is 0. So with this definition, this also implies that G is equal to 0 on the boundary of the region. Okay, so that's the definition of the Green's function. It's defined by putting a negative point charge at W and then taking the induced potential normalized to be 0 on the boundary of the region. And again, this function, you can picture this nicely in your mind. It's 0 on the boundary and it blows up at W. So in particular, by the maximum principle, it's positive everywhere. And we know exactly what its behavior is like. It's a bounded function plus this logarithmic term near W. Now, what is the Green's function good for? Why would anyone introduce it? Well, it gives us a couple of very interesting things. One of them is we can now solve the equation Laplacian of phi is equal to, say, C, where let's say for convenience, C is a compactly supported smooth function in our domain. So somebody gives us an arbitrary charge distribution, and we'd like to solve Laplace's equation. Well, we already have Laplace's equation for a delta function. So actually, let me put a minus 2 pi in here, just for convenience. And the solution is just given by taking phi to be the convolution of this Green's function with c. In other words, you just integrate the function, so phi of z is given by integrating the Green's function g of zw, weighted by the function c of w with respect to the area form dw squared. Integrate that over our region omega. So that's one of the purposes of the Green's function, is to solve this, this equation in general. And as you can imagine, the Green's function is hard to compute explicitly for an arbitrary region, because it implicitly uses this the solution to the Dirichlet problem. But by the same token, it's easy to compute on the unit disk, because we know how to solve the Dirichlet problem on the unit disk. So let's just say what it is on the unit disk. So for omega equals delta, first, what does g of zw equal? Well, first, g of z, 0, should be a function that blows up like this and vanishes on the boundary of the disk. It should blow up when w is 0. Well, in fact, it's just that function, log 1 over the absolute value of z, period. Why does this work? It's because when you're on the boundary of the disk, the absolute value of z is 1, and so this already vanishes. That's the key point. It has the right behavior where the singularity should be, and it already vanishes at the origin. But now once we know this, it's obvious what it is at every point, because the definition of the Green's function was natural. It is in fact a conformal invariant. It only makes use of the notion of the Laplacian and harmonic functions. So if A, or let me call it G, if G is an automorphism of the disk, then the Green's function of g of z and g of w is the same as the Green's function of z and w. And so all we have to do to compute the Green's function at another point is find a function g that moves the origin to that point. So if we use g of z is z plus w over 1 plus w bar z, then that moves this to w, and what we find is simply that g of zw is equal to the log of 1 over the absolute value of g of z. And that's equal to the log of 1 plus w bar z, that's the denominator, but we're taking the reciprocal, and then minus the log of z plus w, and this can be rewritten as the log of, I'm going to factor a w out of this. So this is the log of 1 over w bar minus c plus, well, minus the log of z plus w plus a constant, which is the log of the absolute value of w. So that's the explicit formula for the Green's function on the disk. And we get it just from our knowledge of Mobius transformations. Now, I want to explain this formula because physicists can write this formula down off the top of their head. And here's how they think about it. So we have the unit circle, and we wanted to have a point charge of mass -1 at the point W. Okay, so where is that in our expression? It's here. When Z is, think I made a mistake here. Maybe I wanted everything to be minus W. Yeah, I changed this to a minus sign, didn't I? So I wanted this to be minus here. So this should be minus, minus. Now I think it's correct. Okay, so when Z goes to W, you get your point charge with a minus sign because of this term. But what about this mystery term here? This mystery term corresponds to a positive charge. And where is this positive charge? It's at 1 over W bar. Now, where is 1 over W bar in this picture? Here's the origin. Let me make the picture a little clearer. Here's the origin, here's W. Where's 1 over W bar?
1 over W bar, it's like, it's the same argument as W, but with the radius inverted.
Correct. And does anybody know the name for that point? Or how it's related to the unit circle?
Something to do with circular inversion or something like
Yeah,
that.
that's right. It's the reflection of W through the circle. So there is an anti-holomorphic map on the Riemann sphere that takes points inside the circle and moves them to points outside the circle and preserves angles. And it sends 0 to infinity, and it sends W to 1 over W bar. So this point here is the reflection of this point here. And what we've done to find the Green's function is we put a charge of mass -1 here, and then a charge of mass +1 here at the reflected point. And the effect of this is to make the whole configuration symmetric under interchanging 0 and infinity. And because of that, it turns out that the corresponding potential is forced to be constant on the unit circle. So this is what's sometimes called the method of mirrors. If you have a charge inside the disk and you want to get a potential that's 0 on the circle, you take the mirror charge on the outside of the disk, negate it, and then solve Laplace's equation in the whole Riemann sphere for that charge configuration. And it will automatically be a constant on the circle. And then the constant turns out to be log 1 over the absolute value of W. So we get rid of that constant with this term here. Okay, so that's actually not, there's a kind of a physical intuition for why the Green's function for the unit disk has this form. Now, one thing that's kind of interesting about this Green's function, let's look at it in this formula here, is you'll notice that it's symmetric in ZW. In other words, G of ZW is G of WZ. And that turns out to be a general property of the Green's function. Where does it come from? Well, let me just give you a hint. This should remind you of the fact that the Laplacian has the property that when you take the Laplacian of F and integrate it against G, it's the same as taking F and integrating it against the Laplacian of G. And this equation, the symmetry of capital G, is equivalent to saying that if we take G and convolve with F and then integrate against G, that's the same as taking F and convolving G against G. So in other words, this symmetry is tantamount to the statement that G is a self-adjoint operator. But what is the operator G? Well, as you can see from this discussion here, what the whole point of G is that the Laplacian of G applied to C gives you back C. So in other words, morally, G is the inverse of the Laplacian. And now you might say, well, that doesn't make sense because if all you know is the Laplacian of a function, you can't recover the function because you could add any harmonic function to it. Or you could also say the Laplacian is not invertible because the harmonic functions are killed by the Laplacian. So you'll never get them if you try to invert. But remember, what we've done is we've restricted to functions that vanish on the boundary of our region. And if you have a harmonic function that vanishes on the boundary, it's identically equal to 0. So this is really the inverse of the Laplacian, restricted to functions equal to 0 on the boundary of omega. And then the inverse turns out to be essentially well-defined, and the fact that this is self-adjoint implies that this is self-adjoint. That's the heuristic idea of where the symmetry comes from. Okay. So now towards the definition of capacity. So capacity. So we place ourselves in the previous situation, but this time I want to take omega to be the outside of a compact set. And this compact set K will be the union of finitely many Jordan domains. K1 up to Kn. And then omega will be the outside of K, and plus the point at infinity. So for this picture, it's good to think on the Riemann sphere. Here's the point at infinity. It's inside of omega. And then omega itself, then we have a couple of disks somewhere. That's K. And then omega itself is the outside of these disks. And so up to a Mobius transformation, this is the same as the situation we were talking about before. We've just normalized so that some point in the originally bounded domain omega is now at infinity. But the Green's function is still perfectly defined. And then we define g of z, or gk of z, I'll just call it g of z, to be the Green's function g of z infinity for the region omega, which is the Riemann sphere minus this compact set K. So in other words, we put a point charge of mass -1 at infinity, and then we solve for the harmonic function that's 0 on our compact set K and blows up, goes to plus infinity at infinity. So what does this Green's function look like? So necessarily, g of z looks like the logarithm of the absolute value of z, exactly as before. That's the statement that it blows up to give a point charge at infinity. And then, because of the fact that it's the real part of an analytic function, there's a constant, gamma, which I'm going to write negatively, and then plus something that tends to 0 at infinity. So let's look at an example. First, the disk of radius r. Let's take that to be K. Always start with the simplest example. What is the Green's function here? Well, it should blow up like the log of the absolute value of z, but it has to vanish on the boundary of the disk of radius r. So for this K, g of z is nothing but the log of the absolute value z, but we divide by r. We divide by r so that g restricted to the circle of radius r is equal to 1. And what we get is exactly the log of the absolute value of z minus the log of r. Now, of course, for the disk of radius r, the obvious definition of its diameter, its transfinite diameter, its polynomial diameter, they both came out to just be the ordinary radius r. So we define the capacity of K to be this in terms of this constant that appears here, and this minus gamma. We see that for a disk of radius r, it's given not by r, but by the logarithm of r. And so we just take it to be e to the gamma. And that is the definition of the capacity of K. So again, to find it for a given compact set, we have to find this Green's function, which is equal to 0 here. It's positive in the region. It has a logarithmic singularity at infinity. Then we see what the first non-trivial term is in its expansion asymptotics near infinity. And then we take e to that constant. Okay, sounds kind of hard. But actually, there's one case where it's very geometric and where it's very well known to us. And that's the case where K is connected. So here's a theorem. Suppose K is connected. And F, or better yet, well, sorry, this is not, let me say this more intelligently. Suppose K is connected and the Riemann sphere minus K is connected. And K is not just one point. Then there exists a Riemann map F from the complement of K to the complement of the unit disk. But also, we could scale the unit disk so it becomes the disk of any radius we choose by just composing with a dilation in the target. And we can, with R here is chosen, so f of z equals z plus lower order terms when z is close to infinity. So in other words, we try to find the Riemann map that turns the complement of K into the complement of the disk of radius r, and that looks as much like the identity as possible in the sense that it's asymptotic to the identity at infinity. Such a Riemann mapping always exists by the Riemann mapping theorem, but this value of r changes depending on what K is. It has to do with the first term in the power series for the Riemann mapping at infinity. Then the capacity of K is equal to R. So to put it differently, if you take the disk of radius R and you apply any conformal map to the outside with the property that it's approximately the identity at infinity, you don't change the capacity of the set. So we can easily now go beyond this case that was kind of trivial. And for any Riemann mapping that we understand, we can compute the capacity of K. So here's a nice example. What is the capacity of the interval from -2 to 2? Well, we know a map from the complement of the unit disk, we know a map from let me say it that way. We know a map from the complement of the unit disk, the outside here, to the outside of the interval from -2 to 2. Namely, f of z is z plus 1 over z. And this mapping is obviously asymptotic to z at infinity. And so it follows that the capacity of the unit disk is the same as the capacity of the interval from -2 to 2. And since this is 1, this is also equal to 1. Now what's the proof? What happened to the Green's function? Well, notice, by the way, I interchanged F and G here. So maybe I should, I interchanged the domain and range here. Maybe I should call this G. This is the inverse of the Riemann mapping that goes from the outside of K to the outside of the unit disk. In any case, if G oscillates the identity at infinity, then so does its inverse. Okay, so the proof of the theorem is really one line. The proof is that we know the Green's function for the region K, namely G of Z, the Green's function at infinity for K, is given by the logarithm of the absolute value of f of z. Why? Well, f of z is asymptotic to z as z goes to infinity. So the Green's function is asymptotic to the log of z. Now, we also have this r here, but let's do this for the case where r is equal to 1, just for simplicity. Then we have big O, little o of 1 here for the log of the absolute value of f of z. And what happens when z goes towards k? Well, in that case, f of z goes towards the unit circle. And so on the unit circle, the logarithm of z is asymptotic to 1. And so this tends to 0 as z tends to the boundary of k. And therefore, it is the Green's function, and this implicit number gamma here is equal to 0. Okay, so let me say this just a little bit more geometrically, or by drawing a picture. The Green's function is not a mystery when you know the Riemann mapping. So here's a locus where we know the Green's function, the disk of radius 1. The level sets of the Green's function are just round circles. So this is where t is equal to a constant. Now, I could ask you what the level sets are for the Green's function on the outside of the interval from -2 to 2. And the answer is very simple. They're preserved by this mapping F, which is z plus 1 over z. The Green's function is a conformal invariant, so its level sets are canonically attached to the compact set K plus the point at infinity. And so the Green's function for the complement of this interval has as its level sets just the images of the circles under the mapping F. And these level sets, you can check, are exactly ellipses. In fact, they're ellipses with foci at plus or minus 2. And so we know explicitly what the Green's function is whenever we know what the exterior Riemann mapping is. Okay, so that's a beautiful connection, geometric connection between the Riemann mapping and capacity, and it's what allows us to compute it in a great many cases, like this case here. Okay. Now, turns out the Green's function gives us something equally interesting for our compact set K. Oh, by the way, there is a mild objection you could raise at this point. Did anybody notice a logical inconsistency when I started talking about this interval from -2 to 2? What was my assumptions on K when I discussed the Green's function?
Assumed it was a Jordan domain.
Yeah, is the interval from -2 to 2 a Jordan domain?
No, it's like a little case. Sort of.
It has no interior. So I'm sweeping something under the rug, which I will continue to do as we discuss capacity, which is that the discussion makes sense, in fact, for an arbitrary compact set. However, the discussion of the proof of the solution to the Dirichlet problem becomes much more subtle when you have an arbitrary compact set. In particular, the Dirichlet problem doesn't always have a solution, or rather we should change the definition of what a solution means. But let me finesse that here by just saying that if we wanted to find the capacity of a set K we don't understand, say it's a Cantor set, so something fractal like this, what we do is we approximate it by a Jordan domain. So we write K in the following way. We write it as the intersection of sets Kn, where K1 contains K2, contains, etc. And each of these Ki's are Jordan domains, or finite unions of Jordan domains, so finitely many topological disks. And then we define the capacity of K to be the limit of the capacity of Kn. It's easy to show that this is a decreasing sequence, and therefore it exists. So I'm going to be a bit cavalier about that point. We also could have showed that the Dirichlet problem has a solution whenever the Riemann mapping exists. So it certainly works even in the case of the interval from -2 to 2. And in fact, when we discussed harmonic measure, that was all already implicit in our discussion. Okay. There's another beautiful intrinsic invariant of a compact set you get from the discussion of capacity. And this is what's called the equilibrium measure. So this is something we can define again whenever we have a set where the Green's function is defined. So let G be the Green's function, by which I mean, of course, the Green's function at infinity. We call it G of Z to emphasize it only depends on one variable. For the compact set K contained in C, then the Laplacian of G as a distribution is equal to 2 pi times mu, where mu is a probability measure supported on the boundary of K. And this mu is called the equilibrium measure of K, or of the complement of K. Okay, so first let me explain intuitively what this measure means. Well, so of course, as an example, if we take the case of the unit disk, if omega is the unit disk, so K rather is the closed unit disk, then this equilibrium measure is just d theta over 2 pi. And in general, if the boundary of K is smooth, then mu is equal to 1 over 2 pi times the gradient of G, which will be normal to the boundary, times arc length along the boundary. Okay, so let me try to explain intuitively what this gadget is. So we have our smoothly bounded region K, and we have a potential function which is 0 on the boundary, and then at infinity, which I'll draw as if we can see it, we have a point charge of mass -1. And what does the gradient of phi look like? It flows normal to the boundary here because phi is constant on the boundary. And if you follow a streamline, well, the value of phi just gets bigger and bigger, and so you flow off to the point at infinity. Now, by the way, you could apply the Riemann mapping to turn everything into the complement of the unit disk. And then these streamlines would just become the rays orthogonal to the boundary of the unit disk. Now, how do I know that the Laplacian gives rise to a unit charge on the boundary of K? The reason for that is very simple. If I want to know how much charge there is on K, all I have to do is ask myself, what is the flux of the Laplacian of phi, say through a circle of large radius? Remember, the Laplacian is area preserving, and the net flux out of a region tells you how much charge is inside the region. But we know what the flux is going outward because it's the same as the flux going into the point at infinity, except with sign is reversed. So the total flux going outward is the same as minus the charge at infinity, and it's equal to 1. Okay, so what the Green's function is giving you is some sort of charge distribution on the boundary of K. And I think it's important for the point of view of intuition to understand what this charge distribution is. And we will revisit it many times. But first, let me tell you how people who work in electrostatics think about it. Imagine that K is metal. Now, what's special about metal? Does anybody know how electrons behave in a metal as opposed to an insulator?
There's no restriction on their movement.
Yeah, that's right. So the electrons are free to move around inside of the metal. There's no impediment to them concentrating more in one place and less in another place. Now let's think about this potential function phi. Suppose that on the boundary of K, phi were to look like this. Well, that would not be an equilibrium condition for the metal. What would happen is that the electrons that are over here at the top of the potential well would flow down into the bottom of the potential well to try to reduce their energy. And so the reason phi is constant on the boundary is because K is a conductor. Or to put it differently, the condition that phi is constant on the boundary is equivalent to the condition that K is a conductor. So the electrons move around to try to give make the potential constant here. If it's not constant, they would flow to reduce their energy. So the fact that phi is equal to 0 means the electrons have moved into this equilibrium position, and the measure mu records that equilibrium distribution of charge. So it's not hard to believe, and it's sort of obvious by symmetry, that on the unit disk, the equilibrium measure is just proportional to arc length on the disk. But what about on the interval from -2 to 2? So let me just, I won't calculate this, but we could. We know exactly the map from the complement of the unit disk to the interval from -2 to 2. And I was drawing the level sets before. They look like very eccentric ellipses when you get down close to this region, which means that the lines of constant potential get very close together at the tips. So what happens here is the charge distribution is some function of x times dx on the interval from -2 to 2. And the function looks like this. It blows up. The total mass underneath it is 1, but it blows up at the 2 endpoints here. And you can kind of see that from this picture. The gradient is orthogonal to the circle, but the gradient lines get closer and closer towards the tip. And so the charge kind of flows out from the middle of the conductor and it concentrates close to the tip. So these electrons are all trying to repel one another. So they want to get away from the middle and they sort of concentrate near the tip. And that's something you can explicitly calculate using this very simple map, z plus 1 over z. Okay. So let me say a word then about the final theorem about diameters, which is that the capacity of K is equal to the infinity of K, which is the same as R infinity of K. Now it's interesting that for the proof, we don't even need the transfinite diameter. We're just going to prove that the polynomial radius is equal to the capacity. So the proof in one direction is maybe surprisingly easy. So let's suppose the capacity of K is equal to 1. By the way, you can check from our definitions that, like the other functions, the capacity of T times K is the absolute value of T times the capacity of K. So you can always rescale K. Both sides will scale in the same by the same factor. So we might as well reduce to the case where the capacity is 1. So then the corresponding Green's function is log of the absolute value of Z plus no constant plus O of 1. And that means it's given exactly by the convolution of the fundamental solution with the equilibrium measure mu. But we don't really need that information. What we need is the fact that there is, in principle, a constant gamma here, but gamma is equal to 0. And now we let Pn of Z, Z minus A1 to Z minus AN, be a monic polynomial. Okay, now what we're interested in is studying the absolute value of this, and actually to the 1 over n. So let's look at 1 over n times the logarithm of the absolute value of Pn of Z. This is just given by 1 over n times the sum of the logarithms of Z minus AI, where I goes through the roots of Z. So notice that this function is asymptotic to log Z again, just like the Green's function, plus little o of 1. So this is the relationship between polynomials and Green's functions. This is how we get connected to potential theory. The absolute value, the log absolute value of a polynomial is just the potential associated to n point charges, one for each root of the polynomial. And when we take the nth root, it's normalizing so that the total mass of that charge is equal to 1, or so that the potential behaves like log Z at infinity. Okay, so now we have two harmonic functions. Let me call this h of Z. And what we see is that they behave the same way at infinity. So g of Z minus h of Z is harmonic at infinity. So this is harmonic on the complement of K, including the point at infinity. So by the maximum principle, oh, and it also, let me call this also g of infinity minus h of infinity is equal to 0. So we have a function that's harmonic, and it's equal to 0 at the point at infinity, and then on our compact set K, it has some fluctuations. Well, if you ever have a harmonic function that's 0 at infinity, then on the boundary, its maximum has to be bigger than 0, and its minimum has to be less than 0 because of the inequality because of the maximum principle. So it follows that the min on the boundary of K is less than or equal to 0. But the min on the boundary of K being less than or equal to 0, that's something, sorry, that's of g of Z minus K, h of Z. But g of Z is 0 on the boundary. That's the definition of the Green's function. So the min of minus h of z is less than or equal to 0. And so the max over k of h of z is greater than or equal to 0. But that means the max over k of e to the h of z is greater than or equal to 1. And this is just the max of the absolute value of our polynomial to the 1 over n. And so that shows that, little rn is greater than or equal to 1, and therefore little r infinity is greater than or equal to 1, which is the capacity of k. Okay, so next time we'll wrap up capacity, and then we'll go on to discussing the method of extremal length. Okay.